Section 7.4, Scalability and Disposability. Deploying multiple instances of the same application helps in achieving high availability. When the workload is high, it can be distributed across different replicas. When an instance enters a faulty state and can't process requests anymore, it can be deleted and a new one created. This continuous and dynamic scaling of application instances requires stateless and disposable applications, as per the 15-factor methodology. This section will show you what it means for an application to be disposable, how to enable graceful shutdown, and how to scale an application in Kubernetes. Section 7.4.1, Ensuring Disposability, Fast Startup. Traditional applications deployed on application servers take quite some time to start. It's not rare for them to take several minutes before they're ready to accept connections. On the other hand, cloud-native applications should be optimized for starting quickly, taking a few seconds rather than minutes to become ready. Spring Boot is already optimized for fast startup, and each new version is shipped with more improvements. Fast startup is relevant in a cloud environment because applications are disposable and are frequently created, destroyed, and scaled. The quicker the startup, the sooner a new application instance is ready to accept connections. Standard applications like microservices are good with a startup time in the range of a few seconds. On the other hand, serverless applications usually require a faster startup phase in the range of milliseconds rather than seconds. Spring Boot covers both needs, but the second use case might require a bit of additional configuration. In Chapter 16, you'll learn about serverless applications with Spring Cloud Function, and I'll show you how to package them as native images using Spring Native and Graal VM. The result will be an application with almost instant startup time, reduced resource consumption, and reduced image size. Section 7.4.2, Ensuring Disposability, Graceful Shutdown. Having applications start quickly is not enough to address our scalability needs. Whenever an application instance is shut down, it must happen gracefully without clients experiencing downtime or errors. Gracefully shutting down means the application stops accepting new requests, completes all those still in progress, and closes any open resources, like database connections. All the embedded servers available in Spring Boot support a graceful shutdown mode, but in slightly different ways. Tomcat, Jetty, and Netty stop accepting new requests entirely when the shutdown signal is received. On the other hand, Undertow keeps accepting new requests but immediately replies with an HTTP 503 response. By default, Spring Boot stops the server immediately after receiving a termination signal, SIG-term. You can switch to a graceful mode by configuring the server.shutdown property. You can also configure the grace period, which is how long the application can spend processing all the pending requests. After the grace period expires, the application is terminated, even if there are still pending requests. By default, the grace period is 30 seconds. You can change it through the spring.lifecycle.timeout per shutdown phase property. Let's configure graceful shutdown for catalog service. We could do that via environment variables or set it as a default configuration. We'll go with the second option. Open the application.yml file located in the catalog service/src/main/resources folder and update the configuration as follows.
See this code?
Since we've modified the application source code, we need to build a new container image and load it into Minikube. That's not very efficient, is it? Later in the chapter, I'll show you a better way. For now, follow the procedure I described earlier to package catalog service as a container image, ./gradle-w boot build image, and load it into the Kubernetes cluster we are using for Polar Bookshop, Minikube image load catalog, service-profile Polar. After enabling application support for graceful shutdown, you need to update the deployment manifest accordingly. When a pod has to be terminated, for example during a downscaling process or as part of an upgrade, Kubernetes sends a SIG-term signal to it. Spring Boot will intercept that signal and start shutting down gracefully. By default, Kubernetes waits for a grace period of 30 seconds. If the pod is not terminated after that period, Kubernetes sends a SIGCAL signal to force the pod's termination. Since the Spring Boot grace period is lower than the Kubernetes one, the application is in control of when it will terminate. When it sends the SIG-term signal to a pod, Kubernetes will also inform its own components to stop forwarding requests to the terminating pod. Since Kubernetes is a distributed system, and the two actions happen in parallel, there is a short time window when the terminating pod might still receive requests, even if it has already started the graceful shutdown procedure. When that happens, those new requests will be rejected, resulting in errors in the clients. Our goal was to make the shutdown procedure transparent to the clients, so that scenario is unacceptable. The recommended solution is to delay sending the SIGTERM signal to the pod so that Kubernetes has enough time to spread the news across the cluster. By doing so, all Kubernetes components will already know not to send new requests to the pod when it starts the graceful shutdown procedure. Technically, the delay can be configured through a pre-stop hook. Let's see how we can update the deployment manifest for catalog service to support a transparent and graceful shutdown. Open the deployment.yml file located in catalog service/K8s and add a pre-stop hook to delay the SIGTERM signal by 5 seconds.
Listing 7.4. Configuring a delay in Kubernetes before the shutdown starts.
Finally, apply the updated version of the deployment object with kubectl apply-fkate/deployment.yml. Kubernetes will reconcile the new desired state and replace the existing pod with a new one for which graceful shutdown is fully configured. Note: when a pod contains multiple containers, the SIGTERM signal is sent to all of them in parallel. Kubernetes will wait up to 30 seconds. If any of the containers in the pod are not terminated yet, it will shut them down forcefully. Now that we've configured the graceful shutdown behavior for catalog service, let's look at how to scale it in a Kubernetes cluster. Section 7.4.3, Scaling Spring Boot Applications. Scalability is one of the main properties of a cloud-native application, as you learned in Chapter 1. To be scalable, applications should be disposable and stateless, as per the 15-factor methodology. We handled disposability in the previous section, and catalog service is already a stateless application. It has no state but relies on a stateful service, the PostgreSQL database, to permanently store the data about books. We scale applications in and out, and if they weren't stateless, we would lose the state every time an instance is shut down. The general idea is to keep the application stateless and rely on data services for storing the state, just like we do in catalog service. In Kubernetes, replication is handled at the pod level by a replica set object. As you saw earlier, deployment objects are already configured to use replica sets. All you need to do is specify how many replicas you want to be deployed. You can do that in the deployment manifest. Open the deployment.yml file located in catalog service/K8s and define how many replicas of the pod running catalog service you want. Let's go with 2.
Listing 7.5. Configuring number of replicas for the catalog service pod.
The replication is controlled using labels. In listing 7.5, the configuration instructs Kubernetes to manage all pods with the label app equals catalog service so that there are always 2 replicas running. Let's check it out. Open a terminal window, navigate to the catalog service folder, and apply the updated version of the deployment resource.
See this code?
Kubernetes will realize that the actual state, 1 replica, and the desired state, 2 replicas, don't match, and it will immediately deploy a new replica of catalog service. You can verify the result with the following command.
See this code?
In the age column, you can tell which pod is the one that has just been deployed to achieve a state with 2 replicas. What happens if one of them terminates? Let's find out. Pick one of the 2 pod replicas and copy its name. For example, I might use the pod named this. Then, from a terminal window, delete that pod with the following command.
See this code?
The deployment manifest declares 2 replicas as the desired state. Since there is now only 1, Kubernetes will immediately step up to ensure the actual state and the desired state are aligned. If you inspect the pods again with kubectl getpods-l app equals catalog service, you will still see 2 pods, but one of them has just been created to replace the deleted pod. You can identify it by checking its age.
See this code?
Under the hood, a replica set object keeps checking the number of replicas deployed and ensures they are always in the desired state. That's the basic functionality on top of which you can configure an autoscaler to dynamically increase or decrease the number of pods, depending on the workload, and without having to update the manifest every time. Before moving on to the next section, make sure you change the number of replicas back to 1 and clean up your cluster by removing all the resources you have created so far. First, open a terminal window, navigate to the Catalog Service folder where you define the Kubernetes manifests, and delete all the objects created for Catalog Service.
See this code.
Finally, go to your Polar deployment repository, navigate to the Kubernetes Platform Development folder, and delete the PostgreSQL installation.
See this code.